let me just quickly review things that we have done so far, okay? All right, so what we found is that classical electrodynamics can be formulated in two sets of equivalent variables. Okay, so if you look at classical electrodynamics, which is a very, very beautiful subject, and at some point in my life I'd hope to teach it, can be formulated in terms of the electric field, which is a 3-vector, which is a function of space-time, and a magnetic field, which is also a 3-vector, which is a function of space-time. And those of you who have done a little bit of special relativity and how electrodynamics can be formulated in terms of special relativistic variables know that these two things combine in a rank 2 antisymmetric covariant 4-dimensional tensor called F mu nu. Okay, so this is called the Maxwell tensor. But we won't go into that in this class. Okay, so this is one way of formulating classical electrodynamics in terms of these variables. Another way of formulating classical electrodynamics is through another set of variable, which is the scalar potential and the 3-vector potential. Okay, and these two, or these 4 components in a special relativistic covariant language become part of a 4-dimensional vector potential. Okay, so this is called the vector potential. It's also called the gauge potential. Now, one of the differences between these two formulations is that if you formulate electrodynamics in terms of E and B, there is really no ambiguity. You know, these are essentially the way fields are described, fields are measured in terms of force, and we know that we can measure it very directly. Whereas potentials are measured quite indirectly. They're actually measured in terms of their derivatives and how they give rise to forces. For example, these the scalar potential and the vector potential are related to the electric field and the magnetic field via these formulae. In some sense, this is, well, in every sense, this is the definition of the potentials. Okay, so if you integrate these equations, you can find the definition of the potential. Okay. Now, one of the things about the gauge potential is that they're not unique. So gauge potentials, if you make a gauge transformation, you get a different looking potential, but which is gives rise to the same physics. Okay, so in some sense, this is a redundancy in description. So phi, if you change phi by, say, phi prime, where phi prime is the old phi minus 1 over c, this is dimensional, on dimensional grounds, del lambda by del t, where lambda is a scalar function of space-time, and a goes to, say, a prime, the 3-vector potential, is the old vector potential plus the gradient of the same scalar function, then you can check that E and B are unchanged and your physics remains unchanged. So these are called gauge transformation. And sometimes this is called gauge symmetry. But the application of the word symmetry in this case is erroneous. A symmetry in physics means that you make a transformation on the system, an active transformation usually. Here, you're actually not making a transformation on the system. And in physics, symmetry means when you make an active transformation of your system, something such as the energy remains unchanged. That physical transformation of the system is a symmetry of your system. For example, we talked about translational symmetry, right? Remember translational symmetry? We talked about systems having translational symmetry. And we also talked about systems having rotational symmetry, right? And if the system has, say, rotational symmetry, there's a conserved quantity, and that quantity is called angular momentum. Remember that if my system has rotational symmetry, then the Hamiltonian commutes with all the generators of rotation. And this means that under time evolution of the system, the expectation value of, say, these operators in any state is constant, right? And therefore, we have angular momentum conservation. Similarly, translational symmetry, you can show, leads to the conservation of linear momentum, okay? But these symmetries don't, so these so-called symmetries, the gauge symmetries, do not lead to any conserved quantities. And in that sense, they are not really symmetries. They are more like a huge redundancy in description, okay? So this is something you will see a lot in physics. In physics, there are real symmetries like these guys, and there are fake symmetries, which are gauge symmetries. You will see that in all the important physical theories, such as general relativity and stuff like that. Okay, so this is a new concept. I'm just telling you about it. It's not really essential for our lecture, but I just wanted to. Okay, so I'm going to cut to the chase and tell you review what we did in the last lecture. So in the last lecture, we found how, under a gauge symmetry, how quantum objects behave. So, under a gauge symmetry, so for every gauge symmetry is specified by a scalar function lambda, right? So under such a gauge symmetry, we can define an object, a function, which is the exponential of the I times the charge lambda, this lambda, divided by h bar c. And these gauge function under a gauge symmetry, what happens is that my states in the quantum system changes as a goes to a tilde, where a tilde is given by g acting on alpha, sorry. And we also saw that the transformation of the operator, say the position operator, any operator transforms like this, but the position operator further is invariant under this gauge transformation, so it doesn't change. On the other hand, the momentum operator under a gauge symmetry, does not remain invariant, but changes to the momentum operator, sorry, this is vector, plus Q over C gradient of lambda. Okay.
So could you please explain the transformation of the position and why does it change? I think I got a bit confused.
So why it is invariant?
Yes, sir.
Okay. So what we did is that, we guessed, I gave you this expression, and what we did is that in the last class, we used the fact that the momentum operator is essentially minus I h bar gradient. And if you apply that, then, like in general, any operator under a gauge transformation is going to transform in this way. And that comes from the requirement that if I take the expectation value of any operator, then under a gauge transformation, what happens is that, okay, so the requirement is that it should be gauge invariant, any physical observable. So that means that this should be equal to alpha tilde O alpha tilde, okay? So that is what leads to this sort of transformation property. And then for the momentum, what we did is that we guessed what G was, and then with P given in this position representation, we derive this. But since X is itself in the position representation nothing but a number, it commutes with this function, which is a scalar function. And therefore, we have this transformation law for X, okay? That it is invariant, whereas the momentum is not invariant.
Oh, I think, sir, does it come from the fact that lambda is only a function of space and time? Like this operator?
Yeah, it is a function of space and time. I don't know why you said only, but there's no other functional dependence to be had anyway. So yeah. Is it clear?
Yes, sir.
Okay, good. All right, so yeah, so when we do these transformations, although the Hamiltonian does not look gauge invariant, but what happens is that the Schrodinger equation remains invariant, So the Schrodinger equation of a charged particle is given by I h bar, the time derivative, equal to P minus Q over C of A whole squared divided by 2m acting on psi minus Q phi acting on psi. And this remains invariant under the gauge transformation. Okay, so this is a review of what we did last time. Any questions so far?